It's hard to imagine a world without coordination compounds. Coordination compounds have been used from the earliest times as dyes and pigments. Nowadays, they are used as sequestering agents, that is, for the effective removal of objectionable ions from solution in industrial processing. Example: ethylene diamine tetraacetic acid, in short, which is known as EDTA, is used to soften hard water, which is responsible for scaling of boilers, and also used in extraction of metals. They are also used in analytical chemistry as well. You have already encountered many uses during the laboratory practicals, such as for color tests, gravimetric analysis, complexometric titrations, and as masking agents. Moreover, in the field of bioinorganic chemistry, they occur as naturally occurring complexes, such as hemoglobin, which is a coordination compound of iron, chlorophyll, which is a coordination compound of magnesium, vitamin B12, which is a coordination compound of cobalt. In chemotherapy, cis-diamine dichloride platinum 2, that is, cis-PtCl2 NH3 whole twice, is used as an anti-tumor drug.
ਵਿਦਿਆਰਥੀਓ, ਤੁਹਾਡਾ ਅੱਜ ਦੀ ਕਲਾਸ ਜੋ ਕਿ ਕੋਆਰਡੀਨੇਸ਼ਨ ਕੰਪਾਊਂਡਸ ਬਾਰੇ ਹੈ ਵਿੱਚ ਸਵਾਗਤ ਹੈ। ਹੁਣ ਤੁਹਾਨੂੰ ਉਤਸੁਕਤਾ ਹੋਏਗੀ ਕਿ ਕੰਪਾਊਂਡਸ ਕੀ ਹੁੰਦੇ ਹਨ, ਕਿਵੇਂ ਬਣਦੇ ਹਨ ਅਤੇ ਕਿੱਥੇ ਮਿਲਦੇ ਹਨ। ਇਸ ਤਰ੍ਹਾਂ ਦੇ ਸਾਰੇ ਸਵਾਲਾਂ ਦੇ ਜਵਾਬ ਇਸ ਕਲਾਸ ਵਿੱਚ ਦਿੱਤੇ ਜਾਣਗੇ। ਪਰ ਅੱਜ ਦੇ ਇਸ ਪਾਠ ਵਿੱਚ ਅੱਗੇ ਵਧਣ ਤੋਂ ਪਹਿਲਾਂ ਆਓ ਅੱਜ ਦੇ ਵਿਸ਼ੇ ਦੇ ਲਰਨਿੰਗ ਆਬਜੈਕਟਿਵਸ ਜਾਣ ਲਈਏ।
On completion of this topic, learners will be able to define coordination compounds and the terms related to them, distinguish between coordination compound and double salts, discuss rules for naming coordination compounds, write postulates of Werner's coordination theory.
Children, coordination compounds are a special class of compounds in which the central metal atom is surrounded by ions or molecules beyond their normal valency. These are also called coordination complexes. The chemistry of coordination compounds is an important and challenging field of modern inorganic chemistry. These compounds are widely present in minerals, plants and animals and play many important functions. What is a coordination compound? Children, chemically speaking, a coordination complex is the product of a Lewis acid-base reaction in which ligands bond to a central metal atom or ion by coordinate covalent bonds. Before going ahead, let us have a look at the definitions of some important terms pertaining to coordination compounds. First one is coordination entity. It constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. For example, in the shown complex COCl3 NH3 whole thrice, the entity in the square bracket is a coordination entity in which the cobalt ion is surrounded by 3 ammonia molecules and 3 chloride ions. Next is central metal atom or ion. it is Lewis acid, thus can accept electron pairs from Lewis bases. A fixed number of ions or groups are bound in a definite geometrical arrangement around it. Next is ligand. It is a Lewis base which contains at least one pair of electrons to donate to a metal atom or ion. In other words, ligands, also called complexing agents, are ions or molecules bound to the central atom or ion in the coordination entity. These may be simple ions such as chloride ion, small molecules such as water or ammonia, larger molecules such as ethane 1, 2, diamine, that is H2, NC, H2, CH2, NH2, or even macromolecules such as proteins. Next is donor atom. Within a ligand, the atom that is directly bonded to the metal atom or ion is called donor atom. Next is coordinate covalent bond. Is a covalent bond in which one atom, that is the donor atom, supplies both electrons. Moreover, the coordination entity carrying a net charge is called a complex ion. Let us now revise these terms with the help of an animation. Here Ag positive represents central metal ions, that is Lewis acid. NH3 represents ligand, that is Lewis base. Nitrogen is donor atom. Arrows represent coordinate covalent bonds. NH3, Ag, NH3 whole positive represents complex ion. Next term is coordination sphere. The central atom or ion and the non-ionizable ligands attached to it are enclosed in square bracket, constitute a coordination sphere. Another related term is counter ions, that is the ion that balances charge of complex ion and is ionizable, that is groups written outside the bracket. For example, in the shown complex K4 FeCN6, the coordination sphere is FeCN whole 6 4 negative, and the counter ion is potassium ion. Another term is coordination number, that is the number of ligands or donor atoms to which the metal is directly bonded. For example, in the shown complex ions PtCl6 2 negative, NiNH3 whole 4 2 positive, the coordination number of platinum and nickel are 6 and 4 respectively. Next is coordination polyhedron, that is the spatial arrangement of the ligand atoms which are directly attached to the central atom or ion defines a coordination polyhedron about the central atom. For example, CONH3 whole 6 3 positive is octahedral, NiCO4 is tetrahedral, and PtCl4 2 negative is square planar. Let us have a look at the shapes of different coordination polyhedra. These are octahedral, tetrahedral, square planar, trigonal, bipyramidal, and square pyramidal. Here M represents the central atom or ion and L represents unidentate ligand. Next is oxidation number, which is the charge the central atom would carry if all the ligands attached to it are removed along with their electron pairs. It is represented by a Roman numeral in parentheses following the name of the coordination entity. For example, oxidation number of copper is CuCN whole 4 3 negative is +1 and it is written as Roman 1 as shown on the screen. To conclude, coordination compounds are distinct chemical species. Their properties and behavior are different from the metal atom or ion and ligands from which they are composed. Let us now discuss about the type of complexes. On the basis of charge complexes can be of three types. These are cationic complexes in which the complex ion has a positive charge. For example, CONH3 holds 3 positive. This complex is cationic. Anionic complexes in which the complex carries a negative charge. For example, AgCN2 negative, this complex is anionic. Neutral complex are those complexes which do not carry a charge. For example, NiCO4, this complex is neutral. On the basis of donor atoms, complexes can be of two types. These are homoleptic complex, complex in which a metal is bound to only one kind of donor groups. For example, CONH3 holds 3 positive. This complex is homoleptic. Heteroleptic complex, complexes in which a metal is bound to more than one kind of donor groups. For example, CONH3 4 Cl2 positive. This complex is heteroleptic. Let us now discuss the differences between coordination compounds and double salts. Children, do you know that both double salts as well as complexes are formed by the combination of two or more stable compounds in stoichiometric ratio? However, double salts lose their identity and dissociate into simple ions completely when dissolved in water, and also show properties of constituent compounds, whereas coordination compounds do not. Let me explain this with the help of an example.
Mohr's salt or ammonium iron sulfate is a double salt of iron sulfate and ammonium sulfate with formula FeSO4 NH4 twice SO4 into 6 molecules of water. Mohr's salt dissolves in water and gives characteristic properties of constituting ions, that is ferrous Fe2 positive, ammonium NH4 positive and sulfate SO4 2 negative ions. FeSO4 NH4 whole twice SO4 gives Fe2 positive aqueous plus 2 NH4 positive aqueous plus 2 SO4 2 negative aqueous. Thus, the double salts are stable in solid state but break up into constituents when dissolved in water as shown on the screen. But coordination compounds, on the other hand, retain their identities in the solid state as well as when dissolved in water or any other solvent. Their properties are completely different from constituents, that is, from metal ions or molecules. For example, NiNH3 whole 6 Cl2 does not show properties of nickel chloride NiCl2 or ammonia NH3. Moreover, in double salts, the constituting salts are of ionic nature, but in coordination compounds, the species present in the complex part are linked with metal atom or ion by coordinate bond. Further, a metal atom exhibits primary valency in the formation of its double salt, but exhibits its secondary valency in the formation of its complex ions.
Thus, points of differences can be based on the following: identity in solution, properties of product with respect to constituent compounds, nature of bonding, kind of valency. Children, let us now discuss rules for naming coordination compounds. For naming the coordination compounds, principles of additive nomenclature is employed. Thus, the groups that surround the central atom must be identified in name. Then they are listed as prefixes to the name of the central atom along with appropriate multipliers. Let us first discuss the order of naming of ions. The cation is named first, whether it is simple or complex, and then the anion is named. Let us take an example. CONH3(6)Cl3. This complex is named as hexaamine cobalt 3 chloride. K2PtCl6. This complex is named as potassium hexachloroplatinate 4. For non-ionic or molecular complexes, one word name is given. CuNO2(3) NH3(3) triamine trinitrocobalt 3. Naming of ligands. Negative ligands end in O. Let us take an example. Cyanide, that is Cn negative, is written as cyano. Carbonate, that is CO3(2) negative, as carbonato. Sulfite, SO3(2) negative, as sulfito. Neutral ligands are generally named as molecules, with certain exceptions like ammonia NH3 is written as amine, water H2O as aqua, carbon monoxide CO as carbonyl, etc. Positive ligands end in em. For example, NO positive is written as nitrosonium, NH4 positive is written as ammonium, H3O positive is written as hydronium. Organic free radicals, when act as ligands, are named as usual. For example, methyl is written as shown on the screen. Let us now learn how to write the prefixes. If several ligands of same type are present, the prefix di, tri, tetra, penta and hexa are used for 2, 3, 4, 5 and 6 ligands respectively. If the name of polydentate ligand includes a number, or for complex ligands like methylamine, the prefix bis, tris and tetrakis are used. Let us now learn how to set the preference order. All ligands are named in alphabetical order. The prefix di, tri are not considered. For example, PtClNO2 NH3(4) SO4 tetraamine chloronitroplatinum 4 sulfate. We now come to naming the complex. Ligands are named first, followed by the metal atom. The ending of the name of the metal depends on the nature of the complex ion. If the complex ion is a cation or non-ionic, the name of the central metal ion is written as such, followed by its oxidation state, indicated by Roman numerals in parentheses. For example, CuNH3(4) SO4. This complex is named as tetraamine copper 2 sulfate. PtCl4 NH3(2). This complex is named as diamine tetrachloroplatinum 4. If the complex ion is an anion, the name of the central metal atom is made to end in ate. For example, Na3AlF6. This complex is named as sodium hexafluoroaluminate 3. Some important points to be kept in mind while writing the names are: the name of the complex should not begin with capital letter. Secondly, The full name of the complex should be written as one word except in ionic complexes where there is a gap between complex entity and counter ion. इन्ना कुछ सिखण तो बाद हुण तुसी वर्नर्स कोऑर्डिनेशन थ्योरी बारे पढ़ोगे. A Swedish chemist, Alfred Werner, was the first to formulate his idea about the structures of coordination compounds. He prepared a large number of coordination compounds and studied their physical, chemical and isomeric behavior by simple experimental techniques. He observed a series of compounds of cobalt-3 chloride with ammonia. These complexes have different colors and different empirical formulas as shown on the screen. Cobalt chloride complex with 6 ammonia molecules is yellow. Cobalt chloride complex with 5 ammonia molecules is purple. One of the cobalt chloride complex with 4 ammonia molecules is green and another is violet. He observed that some of the chloride ions could be precipitated as silver chloride on adding excess silver nitrate solution in cold, but some remained in solution as shown on the screen. When silver nitrate solution is added to 1 mole of CoCl3 6NH3 solution, 3 moles of silver chloride are formed as might be expected. However, only 2 of silver chloride are formed with CoCl3 5NH3 complex and only 1 mole of silver chloride are formed with CoCl3 4NH3. These observations gave birth to the concept of primary, that is ionizable, and secondary valency, that is non-ionizable. This concept is further explained in this animation.
In a series of complexes of cobalt-3 chloride with ammonia, A, primary valencies are represented by dotted lines. B, secondary valencies are represented by solid lines. C, groups satisfying both primary and secondary valency by solid and dotted lines. Further, on the basis of these observations, he proposed a coordination theory. In recognition of his work, Alfred Werner was awarded Nobel Prize in Chemistry.
Let us now discuss postulates of Werner's coordination theory. The first one is, in the coordination compounds, metal atoms exhibit 2 types of valencies, namely the primary valency and the secondary valency. The primary valency is ionizable, whereas the secondary valency is non-ionizable. In modern terminology, primary valency corresponds to oxidation state and the secondary valency corresponds to coordination number. Next postulate is, every metal atom has a fixed number of secondary valencies, that is, it has a fixed coordination number. Another postulate says, the metal atom tends to satisfy both its primary as well as secondary valencies. Primary valencies are satisfied by negative ions, whereas secondary valencies are satisfied by either by negative ions or by neutral molecules. Next postulate is, the secondary valencies are always directed towards a fixed position in space, and this leads to definite geometry of the coordination compound. In other words, secondary valencies have characteristic spatial arrangements corresponding to different coordination numbers Such special arrangements are called coordination polyhedra. Thus, secondary valency determines the stereochemistry of the complex. On the other hand, primary valency is non-directional. If a metal ion has 6 secondary valencies, these are arranged octahedrally around the central metal ion. If the metal has 4 secondary valencies, these are arranged in either tetrahedral or square planar arrangement around the central metal ion. Now let us discuss limitations of Werner's coordination theory. Though Werner was the first to describe the bonding features in coordination compounds, but his theory could not answer basic whys. These are: number 1, why only a few elements form complex? Number 2, why the bonds in coordination compounds are of directional nature? Number 3, why coordination compounds have characteristic magnetic and optical properties? Due to these limitations, Werner's coordination theory lost its relevance and many new theories were put forward like valence bond theory, crystal field theory, which will be discussed on some other day. So now we come to the end of today's topic. Here is a quick test for you to find out how much you have actually absorbed. My first question is, name the types of compounds in which the central metal atom is surrounded by ions or molecules. And the answer is coordination compounds. My next question is, give 2 examples of biologically important coordination compounds. And the answer is hemoglobin and chlorophyll. Another question is, give an example of coordination compound of cobalt and magnesium. Example of coordination compound of cobalt is vitamin B12 and of magnesium is chlorophyll. Next question is, give an example of a complex ion. CuCl2NH3 whole 4 positive is an example of a complex ion. Here comes another question. What is the formula of Mohr's salt? Is it a coordination compound? And the answer is FeSO4NH4 whole twice SO4 dot 6H2O. No, it is a double salt. My next question is, who is the father of coordination chemistry? The father of coordination chemistry is Alfred Werner, a Swiss chemist. Now answer this one. Give the name of the compounds on which Werner made his studies. And the answer is cobalt compounds obtained by dissolving cobalt chloride in aqueous ammonia. My last question is, in a coordination compound, which valency is ionizable and which valency is not ionizable, and what do they represent? And the answer is the primary valency is ionizable and it represents oxidation state of central metal, whereas the secondary valency is non-ionizable in a coordination compound and it represents coordination number. बच्चों, मैनू उम्मीद है कि तुहानू अज दा ये पाठ काफ़ी दिलचस्प लग्या होएगा। ध्यान देण लई धन्नवाद। अगली बार एक होर नवे विषय नाल फिर मिलांगे। तद तक लई इजाजत दिओ।